Imagine standing on a distant planet, gazing up at the sky as an unimaginable force tears through the fabric of space itself. In an instant, a brilliant flash erupts so intense it outshines entire galaxies, so powerful it sends shockwaves rippling across the cosmos. This isn't science fiction, it's real. Somewhere, right now, the universe is unleashing energies so colossal they defy comprehension. And today, we're counting down the 25 most powerful explosions ever recorded in space. These aren't just fireworks, they're cosmic detonations that rewrite the rules of physics, leaving even the brightest scientists in awe. Think about the loudest sound you've ever heard: a thunderclap, a roaring engine, maybe even a volcanic eruption. Now multiply that by a billion. That's the scale we're talking about. These explosions are so vast they can be detected from billions of light years away, their echoes traveling across time and space to reach us. Some last mere seconds but release more energy than our sun will in its entire lifetime. Others carve out voids in the universe so large they could swallow our solar system without a trace. What causes these cataclysmic events, and what secrets do they hold about the birth and death of stars, galaxies, and perhaps even the universe itself? This is a journey to the edges of known science, where reality becomes stranger than fiction. We'll witness supernovas so violent they outshine their host galaxies, gamma-ray bursts capable of sterilizing entire planets, and collisions between celestial titans that send ripples through space-time itself. Each explosion tells a story of chaos, creation, and the incomprehensible forces shaping our cosmos. So buckle up. By the time we reach number 1, your perspective on the universe will never be the same. The countdown starts now. We begin with the granddaddy of all explosions, the event that started it all. Picture this: an infinitely dense point, hotter and more energetic than anything we can comprehend, suddenly erupting with enough force to forge the entire universe in a fraction of a second. This wasn't just an explosion, it was the explosion, the Big Bang. Scientists estimate this cataclysm unleashed energy beyond calculation, birthing space, time, and all the matter we know in one incomprehensible instant. Imagine squeezing the entire universe, every star, every galaxy, every atom, into something smaller than a single grain of sand. Then, suddenly, it's all ripped apart in a firestorm of creation. That's the scale we're dealing with, but how do we even know this happened? The evidence is written in the sky itself, the cosmic microwave background. This faint glow, lingering like an echo from the dawn of time, is the cooled remnant of that initial blast, still detectable nearly 14 billion years later. Think of it as the universe's oldest photograph, capturing that first moment of expansion when everything was searing plasma, before atoms, before light could even travel freely. What's truly staggering is the sheer violence of that birth. In less than a second, the universe inflated from microscopic to cosmic proportions, stretching space itself faster than the speed of light. And the energy, if you converted all the force of the Big Bang into today's terms, it would outshine all the stars in existence, combined by an unimaginable margin. Yet this wasn't destruction. It was the ultimate act of creation, setting the stage for galaxies, for planets, for life itself. Every atom in your body, every speck of dust in the cosmos, traces back to that one explosive beginning. The Big Bang didn't just shape the universe, it is the universe still expanding, still carrying that initial burst forward into eternity. If the Big Bang was the universe's first explosion, then gamma-ray bursts are its most violent tantrums, brief, apocalyptic eruptions so intense they briefly outshine everything else in the cosmos. And standing at the top of this destructive hierarchy is GRB 080916C, a blast so powerful it redefined what we thought was possible. Discovered by NASA, a Fermi Gamma-Ray Space Telescope in 2008, this monster erupted from a staggering 12.2 billion light-years away. That means the light we're seeing now left its source when the universe itself was just a toddler, only 1.5 billion years old. Despite that mind-bending distance, the burst was so bright Fermi's instruments nearly overloaded trying to measure it. Now, let's put that energy into perspective. In just 60 seconds, JABI 080916C unleashed as much power as 9,000 supernova, exploding simultaneously enough to vaporize entire star systems in the blink of an eye. If you concentrated all the energy our Sun will emit over its entire 10 billion-year lifespan into a single minute, you'd still only get a fraction of this burst's raw destructive force. What makes gamma-ray bursts like this so terrifying? They're cosmic death beams, narrow, focused jets of energy moving at near light speed, capable of sterilizing planets thousands of light years away. Had one of these struck Earth when life was first forming, evolution might have been reset before it even began. Yet within that annihilation lies a paradox. These bursts are also cosmic forges, likely created when massive stars collapse into black holes, spraying the universe with heavy elements needed for new stars and eventually life. The same violence that could erase worlds also seeds the ingredients for new ones. Fermi's detection didn't just record a blast, it captured a fundamental process in the universe's life cycle, proving that even in destruction, creation lurks. Now let's talk about something so extraordinary it defies even our wildest cosmic expectations. A supernova that rewrote the rulebook on stellar explosions. SN 2006 GY wasn't just a dying star. It was a celestial bomb that detonated with the force of 100 ordinary supernova combined, lighting up the night sky with unprecedented brilliance. Discovered in the galaxy NGC 1260, roughly 240 million light-years away, this wasn't your typical star going quietly into the night. Most supernova fade after a few weeks, but SN 2006 GY burned brighter for months, peaking at a luminosity 5 times greater than any supernova ever recorded before it. At its brightest, it outshone its entire host galaxy, a single star momentarily stealing the cosmic spotlight from billions of others. But what made this explosion so different? Scientists believe the culprit was no ordinary star. The leading theory points to a behemoth, a star so massive it flirted with the upper limits of what's physically possible. We're talking about a true titan, potentially 150 times the mass of our Sun, packed with volatile elements like oxygen and neon in its core. When such a star dies, it doesn't just collapse, it self-destructs in a process called pair instability supernova, where matter and antimatter particles spontaneously form in the core, triggering runaway thermonuclear reactions. The result, an explosion so violent it obliterates the star completely, leaving no black hole or neutron star behind, just an expanding cloud of glowing wreckage. What's even more mind-bending is the light curve, the way its brightness changed over time. Unlike the sharp peak and quick fade of normal supernova, SN 2006 GY's light lingered, pulsing like a cosmic heartbeat. This suggests the explosion slammed into dense shells of material ejected by the star earlier in its death throes, creating shock waves that lit up like celestial fireworks. Some astronomers speculate this might have been our first glimpse of a phenomenon once thought purely theoretical, the death of a first-generation star from the early universe. These primordial giants, made purely of hydrogen and helium, could have reached staggering sizes before meeting similarly spectacular ends. If true, SN 2006 GY wasn't just an explosion, it was a time capsule showing us how the universe's first lights may have gone dark. So the next time you look up at a quiet night sky, remember, out there, hidden in the darkness, lurk stellar monsters capable of detonations so vast they momentarily outshine galaxies. And thanks to SN 2006 GY, we now know the cosmos still has surprises up its sleeve. While some cosmic explosions fade into obscurity, the Crab Nebula's birth remains etched in human history. In July 1054, Chinese astronomers recorded a guest star so bright it was visible during daylight for 23 days, an unprecedented spectacle that lingered in the night sky for nearly 2 years before vanishing. What they witnessed wasn't just any stellar death, it was the supernova that sculpted one of the most iconic structures in the cosmos. Fast forward nearly 1,000 years, and modern telescopes reveal SN 1054's aftermath in stunning detail. The Crab Nebula, a 6 light-year wide web of glowing gas filaments, still churns with energy. But here's what makes it extraordinary. Unlike most supernova remnants that slowly fade, the crab keeps pulsing with life. At its heart spins a neutron star, a city-sized stellar corpse rotating 30 times per second, whipping charged particles into the surrounding debris like a cosmic lighthouse. This pulsar's magnetic field, a quadrillion times stronger than Earth's, acts as an eternal power plant, accelerating electrons to near light speed and generating eerie blue gamma-ray halos. The synergy between remnant and pulsar creates something rare, a celestial engine that's been running non-stop since the 11th century. Chandra X-ray observatory images show intricate shockwaves rippling outward, while Hubble captures delicate tendrils of oxygen and sulfur glowing like neon signs. Even the nebula's expansion speed tells a story. The debris races outward at 1,500 kilometers per second, meaning if you'd observed it a lifetime ago, its shape would have been noticeably different. What truly astonishes scientists is how this one event keeps giving. The pulsar's beams sweep past Earth 30 times a second, making it nature's most precise clock until you look closer. Tiny glitches in its rotation reveal the neutron star's crust cracking under immense pressure, offering glimpses into matter denser than an atomic nucleus. Meanwhile, the nebula itself serves as a particle accelerator, producing energies labs on Earth can't replicate. In 2011, gamma-ray telescopes even caught it emitting flares more powerful than theoretical models predicted, proof that 9 centuries later, SN 1054 still has secrets to spill. From ancient court astronomers to modern astrophysicists, the Crab Nebula bridges human curiosity across millennia. It's a time capsule, a physics lab, and a cosmic artwork, all born from a star's final, defiant roar. In the sweltering summer of 1843, sailors navigating the southern seas reported something impossible, a new star blazing brighter than Sirius, appearing where none had been before. But this was no ordinary stellar flare-up. Eta Carinae, a volatile superstar already known for its erratic behavior, had detonated in what astronomers now call the Great Eruption. A cataclysm so violent it temporarily became the second brightest object in the night sky, outshone only by Sirius itself. At 7,500 light-years away, that luminosity is staggering. For context, Eta Carinae pumped out as much visible light in those years as our Sun will over its entire 10-billion-year lifespan. The cause, a death spiral between two stellar titans, a primary star with 90 times the Sun's mass and a smaller companion locked in a deadly gravitational dance. As they swung perilously close in their 5.5-year orbit, the larger star began shedding entire suns' worth of material. The aftermath is just as breathtaking. Unlike a typical spherical nebula, Eta Carinae ejected its guts in 2 opposing jets, sculpting the homunculus nebula, an eerie, hourglass-shaped structure spanning half a light-year. Hubble's razor-sharp images reveal intricate dust lanes and shockwaves frozen in this bipolar explosion, like a cosmic Rorschach test written in stardust. But here's what keeps astronomers awake at night. Eta Carinae isn't finished. The surviving star is a ticking time bomb, its core fusing elements at a breakneck pace. When it finally goes supernova, possibly within our lifetimes, it could unleash a gamma-ray burst pointed straight at Earth. The energy would be equivalent to detonating a nuclear bomb over every square kilometer of our planet's surface, stripping the ozone layer and triggering mass extinctions. Yet for all its destructive potential, Eta Carinae is also a cosmic sculptor. The heavy elements forged in its furnace, oxygen, carbon, iron, will someday seed new solar systems. Its violent beauty reminds us that creation and destruction are two sides of the same celestial coin, written across the sky in light and shadow. Deep in the constellation Indus, an event unfolded that blurred the line between destruction and creation, challenging everything astronomers thought they knew about cosmic cataclysms. Assassin 15 LH wasn't just another flicker in the night sky. It was an explosion so luminous, so violent, it outshone our entire Milky Way by a factor of 20. At 3.8 billion light-years away, that kind of brightness shouldn't even be possible. Yet for months, this mysterious beacon burned with the intensity of 570 billion suns, leaving scientists locked in a heated debate. Was this a star being shredded by a black hole's gravity, or something even more exotic? The initial discovery by the All-Sky Automated Survey for Supernova in 2015 suggested a classic tidal disruption event, a TDE. Picture a star wandering too close to a supermassive black hole, its outer layers stretched into spaghetti like strands by intense tidal forces. As the star's material spirals inward, friction heats it to millions of degrees, creating a brilliant flare that can last for months. But Assassin 15 LH refused to follow the script. Most TDEs peak in ultraviolet and X-rays, yet this monster radiated most of its energy as visible light, with a temperature curve that matched nothing in the known universe. Then came the real shocker. The host galaxy wasn't just any galaxy, it was massive, old, and quiescent, exactly the type of environment where supermassive black holes should be dormant. For a tidal disruption event to occur here would be like finding a volcanic eruption in Antarctica, completely defying expectations. Some researchers proposed an alternative, an exceptionally rare type of superluminous supernova, possibly triggered by a rapidly spinning magnetar injecting energy into the explosion. Others suggested an even wilder scenario, a black hole suddenly awakening after a long slumber and consuming a white dwarf star hole. The smoking gun lay in the light's behavior. Unlike typical supernova, which fade predictably, Assassin 15 LH's brightness plateaued for an astonishing 100 days before gradually dimming, a hallmark of materials steadily accreting onto a black hole. Yet its spectrum lacked the hydrogen signatures common in TDEs, deepening the mystery. Even now, years later, the debate rages on with new theories emerging. Could this be evidence of an intermediate mass black hole, a type long theorized but never conclusively observed? What's undeniable is the sheer scale of destruction. Calculations suggest the exploding object released nearly 10 times more energy than our Sun will emit across its entire lifespan, all in under half a year. If such an event occurred in our galactic neighborhood, the radiation would sterilize planets thousands of light-years away. Yet within that destruction lies a revelation. Assassin 15 LH proves there are forces in the universe we haven't even begun to classify. Whether it's a star meeting its end in a black hole's maw or some new breed of cosmic detonation, one thing is clear: the universe still holds explosions that rewrite the textbooks. On April 27, 2013, the skies erupted with a light show that rewrote the record books. GRB 130427 wasn't just another gamma-ray burst. It was the closest, brightest long-duration GRB ever recorded, blazing from a mere 3.6 billion light-years away. For 30 seconds, this cosmic flamethrower pumped out energy equivalent to 500 million suns, so intense that amateur astronomers could spot its afterglow with backyard telescopes. What made this explosion so extraordinary wasn't just its proximity. It was the perfect storm of circumstances that let us study it like never before. NASA Fermi and Swift satellites caught the initial blast, a pulse of gamma rays so powerful it temporarily blinded their detectors. Meanwhile, ground-based telescopes captured something unprecedented, a supernova signature embedded within the GRB's afterglow. This smoking gun confirmed what theorists had long suspected, that at least some long gamma-ray bursts are the death cries of hypergiant stars collapsing into black holes. The numbers still boggle the mind. In under a minute, GRB 130427 released more energy than our Sun will emit in its entire 10 billion-year lifespan. Its afterglow lingered for weeks, radiating X-rays that helped astronomers trace the physics of relativistic jets' beams of plasma screaming outward at 99.9% light speed. These jets, narrower than a pencil's width at their origin, carved through interstellar gas like cosmic blowtorches, generating shock waves that glowed across multiple wavelengths. Yet the real revelation lay in the debris. Spectra revealed heavy elements like nickel and iron forged in the star's final moments, proof that these explosions are cosmic alchemists, seeding the universe with the building blocks of planets and life. Had this burst occurred in our galactic neighborhood, the radiation would have stripped Earth's atmosphere, triggering mass extinctions. Instead, 3.6 billion years later, its light arrived as both a warning and a gift, a front-row seat to the violent physics shaping our universe. What GRB 130427 taught us goes beyond raw power. It revealed the intricate link between stellar death and rebirth, where the same forces that obliterate stars also scatter the elements that make new ones possible. Every time you see a long-duration GRB flicker to life in the night sky, you're witnessing the luminous funeral pyre of a star massive enough to birth a black hole, and the birth cry of elements that might one day form worlds. In January 2002, a dim star in the constellation Monoceros did something no one saw coming. It erupted without warning, becoming 600,000 times brighter than our Sun in a matter of days. V838 Monocerotis wasn't just another variable star. It was a cosmic mystery wrapped in layers of interstellar dust, creating one of the most visually stunning phenomena ever observed, a light echo that transformed the night sky into a celestial theater. Unlike conventional supernova that blast material outward, V838 Mon's explosion didn't destroy the star. Instead, it swelled into a monstrous red supergiant, its outer layers cooling and glowing like a cosmic lantern. But the real magic happened when that light began bouncing off surrounding dust clouds, illuminating them in expanding rings like ripples from a stone dropped in a pond. The Hubble Space Telescope captured this unfolding drama in unprecedented detail year after year. New shells of dust lit up, revealing structures hidden for centuries. The physics behind this light show is just as mesmerizing. The initial flash traveled straight to Earth, but some light took detours, reflecting off dust layers at different distances, arriving months or even years later. Each echo was a time capsule, showing the explosion's light from different angles. By tracking these reflections, astronomers mapped dust clouds 3,000 light-years away with precision, uncovering filaments and tendrils invisible under normal conditions. What caused the eruption? Theories range from a stellar merger, two stars colliding and merging their cores, to an exotic thermonuclear event in the star's outer layers. The absence of heavy elements typically seen in supernova suggests this wasn't a terminal explosion, but rather a stellar belch of epic proportions. Even now, 2 decades later, V838 Mon remains shrouded in secrecy, its core hidden behind a shroud of cooled gas. This explosion didn't just light up the cosmos, it turned interstellar space into a canvas. For astronomers, those shimmering echoes were more than pretty pictures. They were a new tool for probing the galaxy's hidden architecture, and for the rest of us, they served as a reminder. Even in the void of space, light finds a way to paint its story across the dark. In the year 1006, an explosion tore through the night sky so brilliantly it cast shadows on Earth visible even during the day for weeks. This was SN 1006, arguably the brightest supernova in recorded human history. Chinese, Arab, and even European monks documented the event, describing a celestial visitor brighter than Venus, possibly rivaling the Moon itself. At 7,200 light-years away, that level of visibility is staggering, equivalent to detonating a stellar bomb halfway across our galaxy and still seeing its glare from your backyard. Today, the remnant tells an equally dramatic story. Unlike typical supernova debris that glows from heated gas, SN 1006's aftermath emits light through a far more exotic process: synchrotron radiation. Here's how it works. Particles, accelerated to nearly light speed by the explosion's shockwaves, spiral through intense magnetic fields, releasing energy as eerie blue tendrils visible in X-ray and radio wavelengths. This makes the remnant one of the most efficient natural particle accelerators known, with electrons ricocheting at energies that dwarf anything produced in human-made colliders. Chandra X-ray observatory images reveal the explosion's anatomy in breathtaking detail. Two opposing lobes stretch 16 light-years across, shaped by the dying star's bipolar blast. The shock fronts race outward at nearly 30 million kilometers per hour, hot enough to emit X-rays at temperatures exceeding 50 million degrees. Yet the real surprise lies in the remnant's asymmetry. The southern lobe burns significantly brighter, suggesting the star didn't die uniformly but perhaps suffered a violent interaction with a companion before detonating. Historical records hint at more mysteries. Some accounts describe the supernova changing colors over months, from deep red to gold to pale white, a phenomenon modern astronomers attribute to light scattering through interstellar dust. Others note its sudden disappearance after 2.5 years, vanishing as abruptly as it appeared. This matches current models of Type Ia supernova, where a white dwarf star explodes after siphoning too much mass from a neighbor, leaving no compact remnant behind. What makes SN 1006 truly exceptional isn't just its luminosity, but its legacy. The explosion likely forged over half an Earth mass of radioactive nickel, the element responsible for its months-long brilliance. As that nickel decayed into cobalt and iron, it seeded the surrounding cosmos with heavy elements now embedded in new generations of stars. Meanwhile, the remnant's relentless particle acceleration offers a living lab for studying cosmic rays, some of which may have showered Earth during the supernova's peak. From shadow-casting brilliance to a ghostly X-ray glow, SN 1006 exemplifies how a single stellar death can illuminate the universe both literally and scientifically for millennia. Its light may have faded from human eyes, but its echoes continue shaping our understanding of cosmic violence. In the quiet constellation of Sagittarius, a dead star awoke with a vengeance. On December 27, 2004, SGR 1806-20, a city-sized neutron star with the mass of 2 suns flickered to life for just 1/10 of a second. But that brief flash packed a punch beyond comprehension. In that fraction of a heartbeat, this Magnetar released more energy than our Sun will emit over the next 150,000 years. What makes this explosion so extraordinary isn't just the raw power, it's the physics behind it. Magnetars are neutron stars with magnetic fields so intense they could strip the information off a credit card from halfway across the solar system. SGR 1806-20's field is a quadrillion times stronger than Earth's, twisting its metallic crust like taffy until, snap, it fractures in a starquake. This seismic event triggered a gamma-ray flare so intense it ionized Earth's upper atmosphere from 50,000 light-years away, disrupting radio communications worldwide. The numbers still stagger astronomers. The flare's peak luminosity hit 10 to the 39th power watts, enough energy to power human civilization at its current rate for 10 billion years. For context, if you converted that energy into explosive force, it would equal 1,000 trillion Hiroshima bombs detonating simultaneously, all from an object smaller than Manhattan. But here's where it gets stranger. Unlike supernova that blast material outward, this eruption was focused, a concentrated beam of gamma rays and X-rays shooting from the magnetar's poles. Had Earth lain directly in its path, the radiation could have triggered a mass extinction. Instead, we got a ringside seat to a phenomenon that rewrote our understanding of stellar corpses. The aftermath revealed even more surprises. The explosion actually slowed the magnetar's rotation by a fraction, a braking effect caused by the sheer force of the flare. Meanwhile, the blast wave lit up surrounding gas clouds like a cosmic flashlight, allowing telescopes to map previously invisible interstellar structures. SGR 1806-20's tantrum wasn't just a record breaker, it was a wake-up call. Most magnetars flare weakly every few decades, but this hyperflare suggests these dead stars can harbor even more violent potential. Some theories propose such events might explain mysterious cosmic gamma-ray bursts from the early universe. Others wonder if ancient magnetar flares left radiation scars in Earth's fossil record. What's certain is this: beneath their calm exteriors, these stellar zombies are anything but dead. They're cosmic pressure cookers, twisting magnetic fields like rubber bands until, without warning, they snap, proving that even in the grave, stars can still throw the universe's most spectacular fits. Most people think antimatter belongs in science fiction or high-energy physics labs, not crackling through Earth's thunderstorms. But in 2009, NASA, a Fermi Gamma-Ray Space Telescope, caught something astonishing: lightning bolts producing beams of antimatter shooting into space. This wasn't just another cosmic explosion, it was a violent marriage of terrestrial weather and particle physics, rewriting what we thought possible in our own atmosphere. Here's how it happens. During intense thunderstorms, electric fields near the tops of clouds become so strong they accelerate electrons to near light speed. When these relativistic electrons slam into air molecules, they trigger gamma-ray flashes, bursts of energy so intense they spontaneously create matter and antimatter pairs. Yes, you heard that right. Lightning literally manufactures antimatter. The Fermi telescope detected positrons, the antimatter counterparts to electrons, streaming upward along Earth's magnetic field lines as these gamma rays collided with the atmosphere. For a fraction of a second, our planet became a natural particle accelerator, generating the same exotic physics usually confined to supernova or black hole jets. The scale of these events defies intuition. A single terrestrial gamma-ray flash, or TGF, can release up to 100,000 times the energy of a typical lightning bolt, all concentrated into a pulse lasting less than 1,000th of a second. Scientists estimate that somewhere on Earth, about 500 of these antimatter factories ignite every day, though most go unnoticed. Fermi's detection was special because it captured the aftermath, the telltale signal of positrons annihilating with normal electrons over 300 kilometers above the storm, producing a characteristic gamma-ray signature. What does this mean for our understanding of Earth's atmosphere? For starters, it reveals hidden connections between everyday weather and extreme astrophysics. The same processes generating antimatter in thunderstorms may also occur in the magnetospheres of Jupiter and Saturn, where massive lightning storms rage. Some researchers even speculate that TGFS could influence atmospheric chemistry, potentially creating unusual nitrogen oxides that affect ozone levels. But the real kicker, these antimatter beams might pose a radiation hazard. Airline pilots flying near thunderstorms have reported brief, unexplained radiation spikes, now suspected to be TGFS zapping through their planes. While nowhere near lethal, the doses are measurable, proving that antimatter isn't just an abstract concept, it's a tangible, if fleeting, player in Earth's energy balance. From spawning antimatter to mimicking cosmic particle accelerators, these lightning-born explosions blur the line between earthly and extraterrestrial physics. Next time you see a thunderstorm brewing, remember, hidden in those dark clouds are forces powerful enough to twist the fabric of matter itself, proving that even on our seemingly quiet planet, the universe keeps a few explosive surprises up its sleeve. On an ordinary winter morning in February 2013, residents of Chelyabinsk, Russia, witnessed something straight out of an apocalyptic film, a fireball brighter than the sun streaking across the sky at 19 kilometers per second. This was no illusion. A 20-meter-wide asteroid weighing 13,000 metric tons had just slammed into Earth's atmosphere, detonating with the force of 500 kilotons of TNT, 30 times more powerful than the Hiroshima bomb. What followed wasn't just an explosion, it was a wake-up call to planetary defense agencies worldwide. The physics behind the Chelyabinsk event are as fascinating as they are terrifying. As the rock plunged through the atmosphere, air compressed in front of it like an immovable wall, heating the surface to over 25,000 degrees Celsius. At that temperature, solid rock doesn't just melt, it vaporizes. The resulting explosion at 23 kilometers altitude unleashed a shockwave so powerful it circled the globe twice, registering on infrasound sensors designed to monitor nuclear tests. Windows shattered in 6 cities, injuring over 1,500 people from flying glass, while the heat flash was strong enough to cause sunburns on exposed skin. But here's what stunned scientists: Chelyabinsk wasn't some rare cosmic fluke. Studies later revealed these meter-scale airbursts happen far more frequently than we thought, averaging once every few decades. The reason we don't notice: most occur over oceans or unpopulated areas. What made this event unique was its trajectory, approaching from the sunward side, invisible to telescopes blinded by daylight. Had it entered just 15 seconds later, the debris would have rained down on downtown Chelyabinsk instead of the frozen Lake Chebokol, where divers later recovered a 600-kilogram meteorite fragment. The aftermath sparked immediate change. Satellites designed to spot nuclear detonations recalibrated their sensors for meteor tracking. NASA expanded funding for asteroid detection programs, leading to discoveries like 70% more near-Earth objects in the decade since. Even the broken windows served a purpose. Analysis of the damage helped refine models predicting future impact effects. Perhaps most crucially, Chelyabinsk proved that asteroids don't need to be civilization killers to be dangerous. A relatively small rock, barely the size of a school bus, could devastate a modern city if it arrived at the wrong angle, yet within the destruction lay an unexpected gift. The airburst scattered tons of cosmic dust across the region, tiny fragments containing pre-solar grains older than our sun. These microscopic time capsules, collected from rooftops and snowbanks, offered chemists a direct sample of the raw materials that built our solar system. The same explosion that terrorized a city also delivered pieces of the cosmic puzzle scientists had been chasing for decades. Chelyabinsk wasn't just a meteor, it was a mirror, reflecting both our planetary vulnerability and our growing capability to defend against celestial threats. The next time a similar object approaches, we might not be caught off guard. Early warning systems now under development could give days or weeks of notice, allowing evacuation or even deflection attempts. One thing's certain: when the next big impact comes, humanity won't be just bystanders watching the sky fall. We'll be looking up with telescopes in one hand and contingency plans in the other. On June 30, 1908, a blast ripped through the skies above Siberia with such force that it registered on barometers as far away as England. The Tunguska event, a 12-megaton explosion over the remote Taiga, flattened 80 million trees across 2,000 square kilometers, snapping trunks like matchsticks in a radial pattern that still baffles scientists today. Witnesses described a fireball brighter than the sun, followed by shock waves that threw people off their feet hundreds of kilometers away. For days afterward, night skies glowed eerily across Europe and Asia, so luminous that newspapers could be read outdoors at midnight. What caused this devastation remains one of planetary science's greatest whodunits. The leading suspect, a 60-meter-wide space rock, either a stony asteroid or an icy comet fragment that detonated 5 to 10 kilometers above the ground. Unlike the Chelyabinsk meteor, which left fragments, Tunguska's blast left no crater or obvious debris. The prevailing theory suggests the object vaporized completely in a superheated airburst, its energy transforming instantly into a fireball hotter than the sun's surface. The pressure wave alone packed the punch of 200 Hiroshima bombs, though the remote location spared human lives. But here's where the mystery deepens. Expeditions to the site decades later found microscopic silicate and metal spherules embedded in the soil, hints of the vaporized projectile's composition. Some scientists argue these particles skew more comet-like, rich in volatiles that explain the explosion's ferocity. Others point to the lack of water or carbon isotopes typically tied to icy comets, favoring a porous asteroid that shattered like ceramic under atmospheric stress. The event's legacy extends far beyond academic debates. Tunguska became the wake-up call for planetary defense, proving that even modest-sized objects could devastate regions without warning. Had the explosion occurred 4 hours later, Earth's rotation would have placed St. Petersburg or Stockholm in the crosshairs, a direct hit that could have killed millions. Modern simulations suggest similar events recur every few centuries, raising urgent questions about detection. Perhaps most intriguing are the lingering anomalies. Expedition logs from the 1920s describe strange genetic mutations in Tunguska's regrown trees, while some theorists controversially propose antimatter or even mini black holes as alternative culprits. But the likeliest explanation remains the simplest and most terrifying, a reminder that the universe occasionally lobs rocks at Earth, and next time we might not be so lucky. In July 1994, humanity witnessed something unprecedented, a celestial demolition derby unfolding 500 million miles away. Comet Shoemaker-Levy 9, torn apart by Jupiter's gravity 2 years earlier, returned as a cosmic shotgun blast of 21 fragments, each barreling into the gas giant at 60 kilometers per second. The result, a series of explosions so violent they rewrote our understanding of planetary impacts. The first fragment, designated Fragment A, struck Jupiter's southern hemisphere on July 16th, unleashing a fireball that soared to temperatures over 23,000 degrees Celsius hotter than the sun's surface. Telescopes captured a plume rising 3,000 kilometers above the cloud tops, its dark debris scar visible even through amateur telescopes, but that was just the opening act. Over 6 days, successive impacts created Earth-sized bruises in Jupiter's atmosphere, some lasting for months. Fragment G, the largest at roughly 2 kilometers wide, released energy equivalent to 6 million megatons of TNT, 600 times the world's nuclear arsenal detonating at once. What made these impacts extraordinary wasn't just their scale, it was the science they revealed. For the first time, astronomers observed the chemistry of a cosmic collision in real time. Spectrometers detected sulfur compounds and ammonia ejected from Jupiter's lower atmosphere, while infrared telescopes spotted brilliant hotspots where shockwaves heated the gas giant's interior. The scars acted like windows, exposing layers of Jupiter's atmosphere normally hidden from view. Perhaps most startling was the aftermath. The blackened impact zones, some larger than Earth itself, persisted for nearly a year, swirling in Jupiter's turbulent winds like cosmic tattoos. Hubble's images showed intricate ripple patterns, evidence of seismic waves racing across the planet at supersonic speeds. Meanwhile, the event offered a sobering preview of what might happen if a similar comet struck Earth. Had Fragment G hit our planet instead, it would have triggered a global extinction event. Yet within the destruction lay a revelation. Shoemaker-Levy 9 proved that planetary impacts aren't relics of the past, they're ongoing phenomena in our dynamic solar system. Jupiter, with its massive gravity, often acts as a cosmic shield, drawing in hazardous objects that might otherwise veer toward Earth. These impacts also hinted at how water and organic molecules might spread across star systems carried by cometary shrapnel. From fireballs visible across the solar system to atmospheric scars that taught us more about Jupiter than decades of prior observations, this bombardment was a masterclass in cosmic violence. It reminded us that the universe isn't just a static backdrop, it's a living, evolving arena where collisions shape destinies and where even a shattered comet can rewrite the textbooks. On August 17, 2017, the universe announced its presence with a 1-2 punch that rewrote astrophysics forever. At 8:41 in the morning, gravitational wave detectors in Louisiana and Washington state caught a ripple in spacetime, a signal so clean, so textbook perfect that scientists initially suspected it was a test. Then, just 2 seconds later, NASA's Fermi telescope registered a gamma-ray burst from the exact same patch of sky. This wasn't coincidence, it was history, the first confirmed detection of a kilonova, the spectacular merger of two neutron stars 130 million light-years away. The numbers still boggle the mind. These stellar corpses, each packing more mass than our Sun into a sphere barely 20 kilometers wide, spiraled together at 60% light speed, distorting spacetime so violently they shook the universe itself. The collision unleashed gravitational waves equivalent to annihilating 3 suns worth of mass into pure energy, followed by a short gamma-ray burst brighter than 1,000,000 trillion suns. But the real magic happened in the aftermath. For days, telescopes watched as the explosion's radioactive glow revealed something never before seen in real time: the cosmic forge where heavy elements are born. Spectroscopic analysis showed telltale signatures of gold, platinum, and uranium forming in the expanding debris, proof that kilonovas are nature's ultimate jewelers. Calculations suggest this single event likely produced 200 Earth masses of gold alone, scattering precious metals across the cosmos like cosmic confetti. Every gold ring on Earth, every platinum catalyst in a car's exhaust system, they all owe their existence to cataclysms like this. Yet GW170817's legacy goes beyond bling. The precise timing difference between gravitational waves and gamma rays delivered the most accurate measurement yet of the universe's expansion rate. Meanwhile, the lack of an accompanying supernova confirmed that neutron star mergers create at least some heavy elements independently of supernova, a revelation that solved a decades-old mystery about galactic chemical composition. What's truly humbling is how much we nearly missed. Had the merger occurred just a few degrees closer to the plane of our galaxy, its light would have been lost in the Milky Way's glare. Instead, we got front-row seats to one of nature's rarest shows, a spectacle so luminous, so rich with scientific gifts that astronomers are still unpacking its secrets years later. From the gold in our smartphones to the uranium powering reactors, we're literally holding pieces of neutron stars in our hands, forged in explosions like this one across cosmic time. GW170817 wasn't just an explosion, it was a Rosetta Stone, decoding how the universe builds complexity from chaos. In one violent embrace, 2 dead stars became alchemists, proving that even in destruction, creation thrives. And somewhere out there, another pair is spiraling toward their fate, waiting to light up the sky with cosmic gold dust once more. On February 23, 1987, a star detonated so close to Earth that its light reached us without a telescope, the first naked-eye supernova in 383 years. SN 1987 wasn't just another stellar explosion. It was a once-in-a-lifetime cosmic laboratory, offering front-row seats to the death throes of a blue supergiant in the Large Magellanic Cloud, a mere 168,000 light-years away. What unfolded wasn't just a light show, it revolutionized astrophysics. The first clues arrived hours before visible light. 11 neutrinos, nearly massless particles, pinged detectors in Japan, the United States, and Russia. These ghostly messengers, ejected during the star's core collapse, offered something unprecedented: real-time confirmation that supernovae are neutrino factories. For 10 seconds, 1987, released more neutrinos than all the stars in the observable universe combined. A flood so intense it briefly made a nearby tank of cleaning fluid glow with faint radiation. This detection proved what theorists had long suspected, that 99% of a dying star's energy escapes as these elusive particles, not light. Then came the fireworks. Over months, the supernova brightened to magnitude 2.9, visible even from light-polluted cities, but the real surprise was what followed. In 1990, Hubble unveiled 3 glowing rings encircling the blast site, not debris but echoes. The dying star had ejected gas shells centuries earlier. Now, the supernova's ultraviolet flash lit them up like a cosmic fluorescent bulb. These rings became a time machine, revealing the star's pre-explosion tantrums. The inner ring, tilted toward us like a glowing hula hoop, showed where shockwaves slammed into ancient stellar winds at 60 million kilometers per hour. The aftermath kept delivering surprises. By 2004, the blast wave hit the inner ring, heating gas to millions of degrees and sparking X-ray fireworks. Hubble watched as beads of superheated plasma formed along the ring, cosmic pearls strung by turbulence. Meanwhile, ALMA radio telescopes spotted dust rich with carbon monoxide and silicon oxide, the raw materials for future planets. This dust factory challenged assumptions. Astronomers had thought supernova destroyed dust, but 1987 proved they manufacture it too, enough to form 200,000 Earths. Perhaps the most haunting revelation came from the corpse itself. For decades, scientists debated whether the explosion left behind a neutron star or a black hole. In 2019, ALMA spotted a hot blob at the center, possibly the first glimpse of a newborn neutron star shrouded in debris. If confirmed, it's a stellar phoenix hiding in the ashes of its own destruction. What makes 1987 a legendary isn't just its rarity, it's the gift that keeps giving. Every new telescope generation uncovers fresh secrets in its wreckage, from the physics of shockwaves to the origins of cosmic building blocks. This explosion didn't just die, it turned itself into a classroom, teaching us how stars live, how they die, and how their remains seed the universe with the ingredients for life. Even now, 37 years later, its rings still glow, its neutron star, if it exists, still cools, and its lessons still reshape our understanding of cosmic death and rebirth. On August 10, 1972, one of the most bizarre cosmic near misses in recorded history streaked across the American West. The Great Daylight Fireball wasn't your typical meteor. It didn't explode in the atmosphere or crater into the ground. Instead, this 6,000-ton space rock played a game of cosmic skip the stone with Earth's atmosphere, skimming just 58 kilometers above Montana before careening back into space. Witnesses from Utah to Alberta described a fireball brighter than the sun, trailing a smoke plume that twisted into corkscrew patterns as it tore through the upper atmosphere at 15 kilometers per second. What made this event extraordinary was its trajectory. Most meteors burn up or impact within seconds, but this one, roughly the size of a school bus, stayed intact while grazing the atmosphere for a full 101 seconds, covering nearly 1,500 kilometers. Calculations later revealed it dipped deeper into the atmosphere than any other recorded meteor without disintegrating, enduring pressures that should have shattered it. The shockwave rattled windows, and seismographs in Wyoming detected tremors as if from a distant earthquake. Had its angle been just 1 degree steeper, the story would have ended very differently. The energy release was staggering, equivalent to 4 kilotons of TNT, rivaling a small nuclear detonation. But here's the twist: instead of releasing that energy in a single blast, it deposited it across the sky like a cosmic blowtorch, heating the air along its path to thousands of degrees. Satellite data later confirmed the meteor lost about half its mass during the encounter, shedding molten rock as it went. Some of that debris likely rained down as tiny micrometeorites, though no significant fragments were ever recovered. Astronomers reconstructed its origin, a rogue asteroid from the inner solar system, possibly ejected by a Jupiter encounter millennia earlier. Its speed and angle suggest it's still out there, orbiting the Sun with a new, slightly altered trajectory from its close brush with Earth. Modern simulations indicate it'll return eventually statistically within the next 100,000 years, but next time we might not be so lucky. A similar object arriving at a steeper angle could have flattened a city, releasing energy comparable to the Chelyabinsk meteor 30 times over. The Great Daylight Fireball wasn't just a spectacle, it was a masterclass in celestial mechanics. For one brief moment, the skies turned into a laboratory, demonstrating how delicate the balance is between a near miss and a catastrophe. Every day, dozens of smaller rocks follow similar paths unnoticed, but this one chose to put on a show, a brilliant reminder that Earth doesn't exist in isolation, but in an ongoing dance with debris left over from the solar system's violent birth. And sometimes that dance gets uncomfortably close. On September 1, 1859, the skies erupted in a light show so intense it terrified Victorian society. The Carrington event, named after astronomer Richard Carrington, who witnessed its first solar flare through his telescope, wasn't just another aurora. It was the most powerful geomagnetic storm in recorded history, sparked by a solar superflare so violent it hurled a billion-ton cloud of charged particles straight at Earth. Within hours, telegraph systems, the internet of the 19th century, went haywire. Operators reported sparks flying from equipment, some even sending messages with batteries disconnected as natural currents surged through the wires. Newspapers described auroras so brilliant they turned night into day as far south as Cuba and Hawaii, with some eyewitnesses mistaking the crimson glow for distant cities on fire. Fast forward to today, and scientists shudder at the thought of a repeat. A modern Carrington-level storm could induce destructive currents in power grids, frying transformers and plunging continents into darkness for months. Undersea internet cables wouldn't be spared either. Their delicate repeaters, spaced every 50 to 150 kilometers along the ocean floor, are vulnerable to these geomagnetic currents. One study estimates the global economic toll could exceed $2 trillion in the first year alone, with cascading failures disrupting GPS, banking systems, and supply chains. The physics behind this threat is deceptively simple. When a coronal mass ejection, a magnetized plasma bubble from the Sun, collides with Earth's magnetic field, it creates electric fields in the ground. These fields induce currents in anything long and conductive, from 19th century telegraph wires to 21st century fiber optic cables. The 1859 storm was strong enough to set telegraph papers ablaze, but today's infrastructure, with its intricate electronics, is exponentially more sensitive. Yet there's a twist. Not all solar flares are created equal. The Carrington event was a perfect storm, a direct hit from an unusually fast, massive ejection with its magnetic field perfectly aligned to breach Earth's defenses. Recent modeling suggests such extreme storms might occur every 150 years on average, putting us decades overdue. Smaller but still dangerous flares, like the 2003 Halloween storms that damaged satellites and triggered power outages in Sweden, happen far more frequently. The irony: for all our technological advancement, we're arguably more vulnerable than the Victorians. In 1859, the worst outcome was a few fried telegraph lines. Today, a similar storm could collapse the digital backbone of civilization. The silver lining: unlike asteroids, solar storms give us warning roughly 12 to 48 hours from flare detection to impact. Agencies like NOAA Space Weather Prediction Center now monitor the Sun relentlessly, and grid operators can temporarily shut down systems to avoid damage. From telegraph sparks to internet blackouts, the Carrington event stands as both a historical curiosity and a sobering prophecy. It reminds us that the sun isn't just a gentle provider of light, it's a sleeping dragon capable of breathing fire across our wired world with little notice. The question isn't if another superflare will come, but when, and whether we'll be ready when the sky ignites again. In July 2002, the sun unleashed a shockwave of cosmic proportions, a coronal mass ejection so massive it sent a tsunami racing across the solar surface at over 1,000 kilometers per second. NASA and ESA's Solar and Heliospheric Observatory, better known as SOHO, captured the event in unprecedented detail, a towering wall of plasma stretching 100,000 kilometers high, rippling outward like a pebble dropped in a celestial pond. This wasn't just another solar flare, it was a storm front of charged particles with the potential to fry satellites, disrupt power grids, and rewrite our understanding of space weather. What made this explosion extraordinary wasn't just its scale, but its structure. Most solar tsunamis dissipate after a few hours, but this one circled the sun's entire visible hemisphere, lingering for nearly 36 hours. SOHO ultraviolet cameras revealed how the shockwave traveled, compressing and heating the sun's corona to millions of degrees while triggering secondary eruptions along its path. Scientists later calculated the energy release equivalent to 2.4 billion megatons of TNT, or 40,000 times the world's nuclear arsenal detonating at once. Yet the real value of this event lay in its timing. 2002 marked the peak of solar cycle 23, giving astronomers a front-row seat to the sun's most violent behavior at the height of its 11-year activity cycle. The implications for Earth were chilling. Had this eruption been aimed directly at us, the resulting geomagnetic storm could have rivaled the infamous Carrington event of 1859. Modern analyses suggest the plasma cloud contained a twisted magnetic structure particularly effective at bypassing Earth's defenses. Satellite operators watched nervously as the blast narrowly missed our planet, sparing us from potential communication blackouts and GPS failures. But the near miss wasn't just luck, it was a warning. SOHO data revealed something unexpected. These tsunamis can act as early warning systems. The shockwave's speed and trajectory gave about 48 hours notice before the subsequent coronal mass ejection, a revelation that transformed space weather forecasting. Today, solar tsunamis like the 2002 event are cornerstones of space weather prediction models. By tracking their propagation, scientists can estimate the direction and intensity of incoming solar storms, buying precious time to safeguard critical infrastructure. The explosion also solved a lingering mystery: why some coronal mass ejections accelerate particles to near light speed. The answer: tsunami shockwaves act like cosmic particle accelerators, slinging electrons and protons across interplanetary space. Perhaps most astonishing is how this single event bridged the gap between solar physics and practical human concerns. From satellite operators to power grid engineers, the 2002 tsunami proved that understanding the sun isn't just academic, it's existential. As our reliance on technology grows, so does our vulnerability to these cosmic tantrums. The next time a solar tsunami erupts, we might not be spectators. We'll be the ones bracing for impact, armed with lessons from the storm that reshaped space weather science. In July 2012, the sun fired a warning shot across Earth's bow, a coronal mass ejection so powerful it could have scrambled modern civilization back to the pre-digital age. NASA twin stereo spacecraft orbiting the sun like cosmic sentinels captured every terrifying detail as this billion-ton plasma cloud raced through space at over 2,000 kilometers per second. The numbers still send chills down the spines of space weather scientists. Had the eruption occurred just 1 week earlier, Earth would have taken a direct hit, unleashing a geomagnetic storm rivaling the infamous Carrington event of 1859. What made this near miss so alarming? The data didn't lie. Stereo instruments measured the ejection's magnetic field strength at 100 nanoteslas, nearly double the intensity of the Carrington storm. When such a field interacts with Earth's magnetosphere, it doesn't just create pretty auroras. It induces ground currents strong enough to melt copper windings in power transformers, the backbone of electrical grids. Modern simulations suggest the 2012 storm could have knocked out critical infrastructure across North America and Europe, triggering blackouts lasting months and causing up to $2 trillion in global damages. The storm's structure was particularly menacing. Unlike typical ejections that spray particles randomly, this one contained a tightly wound magnetic helix, a so-called rope configuration that punches through Earth's defenses like a battering ram. Stereo ultraviolet cameras revealed how the sun's magnetic field lines twisted into this coiled spring shape before snapping violently, launching the plasma toward where Earth's orbit would soon carry it. By sheer cosmic luck, our planet was on the other side of the sun when the hammer fell. Yet the real revelation came from what happened next. As the ejection plowed through space, it swept up slower solar material like a snowplow, creating a shockwave that accelerated particles to near light speed. These solar energetic particles pose a separate threat. They can penetrate satellite shielding, corrupting computer memory and posing radiation risks to astronauts. The 2012 event proved that even a glancing blow can trigger these particle storms, with fallout detectable across the inner solar system. Perhaps most unsettling is the frequency. Analysis of solar records suggests storms this powerful strike Earth every 150 years on average. The Carrington event was 153 years before 2012. We're statistically overdue, and this time the stakes are infinitely higher. In 1859, the worst damage was fried telegraph lines. Today, an identical storm could collapse financial networks, disrupt global positioning systems, and silence emergency communications during crises. The 2012 near miss wasn't just a close call. It was a fire drill for the apocalypse. Stereo data now fuels advanced warning systems, giving grid operators precious minutes to shut down vulnerable infrastructure before the next big one hits. Because the sun isn't done with us yet, somewhere beneath its broiling surface, magnetic fields are tangling into another time bomb, waiting to remind us how fragile our wired world really is. In late 2019, Betelgeuse, the fiery shoulder of the constellation Orion, did something unprecedented. This red supergiant, normally one of the brightest stars in our sky, dimmed dramatically, losing 2/3 of its usual brilliance over just a few months. Astronomers scrambled as theories erupted. Was this the prelude to a cataclysmic supernova, or something far stranger unfolding in real time? The most tantalizing explanation pointed to an impending explosion. Betelgeuse is a ticking time bomb, a star so massive it's destined to end its life in a supernova visible even in daylight. Its sudden dimming, dubbed the Great Fading, sparked speculation that the star's core might be collapsing, triggering internal convulsions that would soon culminate in a blast visible across the galaxy. Calculations suggested such an event could release as much energy as 100 million suns, outshining the moon for weeks. Amateur astronomers began keeping nightly vigils, their telescopes trained on Orion's shoulder, waiting for history to unfold. But the universe had other plans. By early 2020, Betelgeuse began brightening again, returning to its usual luminosity without fanfare. The truth, revealed by high-resolution imaging from the Hubble Space Telescope, was both more mundane and more fascinating. The star hadn't been preparing to explode, it had simply coughed. Betelgeuse's surface had ejected a colossal cloud of dust, equivalent to twice the mass of our moon, which temporarily obscured its light. This stardust, rich in silicon and carbon, formed a cosmic veil that dimmed the star's glow from our perspective. The event offered an unexpected glimpse into the violent life cycle of red supergiants. Betelgeuse isn't a stable, serene star. It's a seething cauldron of convection cells, with plasma bubbles the size of Jupiter rising and falling in its atmosphere. The great fading likely marked one of these bubbles reaching the surface, cooling into solid particles that drifted outward like ash from a volcanic eruption. This process, repeated over millennia, seeds the cosmos with the raw materials for planets and perhaps life. Yet the supernova theory wasn't entirely off base. Betelgeuse's erratic behavior is exactly what astronomers expect from a star in its death throes. Its core, burning through the last of its nuclear fuel, could collapse at any moment in astronomical terms, any moment meaning tomorrow or 100,000 years from now. When it happens, the explosion will be so bright it'll cast shadows on Earth for weeks, and the neutrinos it releases will outnumber all the atoms in your body. What made this dimming event extraordinary wasn't just the science. It was the reminder that the stars we think of as constants are anything but. Betelgeuse's flicker showed us stellar evolution in action, a preview of the chaos that precedes cosmic rebirth. Whether it explodes next year or millennia from now, one thing's certain: when this giant finally falls, it won't go quietly. It'll blaze across the sky like nothing humanity has seen in recorded history, a final, dazzling testament to the violence that fuels the universe. In May 2020, the cosmos offered a front-row seat to one of the most spectacular acts of celestial self-destruction ever witnessed. Comet Atlas, initially hailed as potentially the brightest comet in decades, didn't meet expectations. It shattered them, literally. Hubble Space Telescope's razor-sharp vision captured the moment this icy traveler, barely a few football fields wide, tore itself apart in a slow-motion explosion 50 million miles from Earth. What began as a hopeful candidate for a dazzling naked-eye spectacle instead became a masterclass in the fragility of cosmic snowballs and their surprising role as solar system gardeners. The breakup unfolded like a cosmic ballet of chaos. Over just 72 hours, Hubble's images revealed Atlas fracturing into 30 distinct fragments, each trailing its own shimmering dust tail. Unlike the quick, violent explosions of supernova or gamma-ray bursts, this was a gradual disintegration, the comet's fragile ices sublimating under sunlight until structural failure ripped it apart. The process exposed pristine material from the comet's interior time capsules dating back 4.5 billion years to the solar system's birth. Spectroscopic analysis revealed surprising chemistry, not just water ice, but traces of cyanide compounds and complex organic molecules, the raw ingredients for life scattered like breadcrumbs across space. But Atlas' real lesson lay in its aftermath. The debris field, stretching over 2,000 miles, became a temporary reservoir of cosmic building blocks. Such breakups are far more than destructive, they're creative acts. Each shattered comet seeds its orbit with dust that may eventually coalesce into meteoroid streams, the source of future shooting stars. Some fragments, nudged by gravity, might even become standalone comets themselves, continuing their journeys on altered paths. This cyclical process explains why Earth's oceans likely owe their existence to ancient cometary, impacts water and organics delivered piecemeal over eons by countless Atlas-like explosions. Hubble's observations also solved a puzzle about comet behavior. Atlas didn't just split, it pulsed, brightening intermittently as fresh ice exposures created brief outbursts. This onion layer model suggests comets aren't uniform ice balls, but stratified time capsules with volatile ices buried beneath inert crusts. When sunlight peels away those outer layers, pressure builds until the comet literally blows its top. The same process might explain mysterious flares in other comets, like the infamous Kohoutek in 1973. What makes Atlas' demise so significant isn't just the event itself, it's the timing. This breakup occurred relatively close to the Sun, where solar heating is intense, but far enough that Hubble could study it in detail without interference. The result, a goldmine of data on how primordial solar system material behaves under stress. Future missions like the Vera C. Rubin Observatory will leverage these insights to predict which comets might fragment next, turning celestial tragedy into scientific opportunity. From Earth's perspective, Atlas' failure to become a brilliant spectacle was a blessing in disguise. Instead of a fleeting light show, we gained enduring knowledge about the delicate architecture of comets and the hidden ways they shape our cosmic neighborhood. Every time a comet shatters, it's not just dying. It's redistributing the very ingredients that might one day help new planets and perhaps new life take root elsewhere in the galaxy. On December 24, 2021, Mars experienced a planetary jolt that sent shockwaves through both its rusty surface and the scientific community back on Earth. NASA InSight lander, stationed near the Martian equator, recorded a seismic event unlike any other. A magnitude 4 marsquark caused not by tectonic shifts, but by a meteoroid slamming into the planet's surface with the force of a small nuclear bomb. This wasn't just another impact, it was a revelation cracking open Mars' secrets in ways no one expected. The numbers alone are staggering. The meteoroid, estimated to be 16 to 39 feet wide, struck Mars' Amazonas Planitia region at 45,000 miles per hour, carving a crater 500 feet across and 70 feet deep. But the real surprise came from what the blast unearthed: massive, boulder-sized chunks of water ice, flung up to 25 miles from the impact site. Before this event, scientists knew Mars had ice, but mostly as thin layers near the poles or buried deep underground. Finding it so close to the equator and in such abundance rewrote assumptions about the planet's water distribution. These gleaming ice blocks, visible in before and after images from NAS, a Mars Reconnaissance Orbiter, were a frozen time capsule preserving clues about Mars' wetter past and potential for life. What made this marsquark extraordinary was the synergy between two missions. InSight's seismometer, designed to study the planet's interior, pinpointed the quake's epicenter. Meanwhile, the orbiter's high-resolution camera captured the fresh scar just 6 miles from the predicted location, a triumph of interdisciplinary detective work. The seismic data revealed details no camera could. The meteoroid likely struck at a shallow angle, spraying debris in a butterfly wing pattern, while the quake's frequency signatures hinted at the subsurface layers it rattled through. The implications ripple far beyond a single crater. Those ice chunks are more than geological curiosities, they're potential resources for future astronauts. Easily accessible water means drinkable supplies, breathable oxygen, and even rocket fuel could be extracted on site, turning Mars from a destination into a potential home. The impact also confirmed that Mars' crust is more fractured and reactive than Earth's, amplifying seismic waves like a bell. This explains why marsquarks, though less frequent than earthquakes, can resonate for hours, a haunting reminder that even a dead planet is still very much alive with activity. From the violence of a cosmic collision to the treasure it uncovered, this event was a masterclass in planetary science. It proved that sometimes, to uncover a planet's secrets, you need something to shake it to its core, literally. And as InSight's sensors fell silent months later, their final gift was this: Mars isn't just a dusty relic, it's a world with ice in its veins, waiting for the next impact, or perhaps the next visitor, to reveal more of its frozen, buried history. The Artemis 1 mission was supposed to be a flawless rehearsal, a stress test for NASA, a next-generation lunar spacecraft. But when the unmanned Orion capsule returned to Earth in December 2022, engineers discovered something unsettling. Hidden beneath the charred surface of its heat shield were unexpected scars, not from the blistering temperatures of re-entry, but from a series of micrometeoroid impacts during its 25-day journey around the Moon. These tiny space bullets, some no larger than grains of sand, had punched deep into the shield's critical outer layer, exposing vulnerabilities that could jeopardize future crewed missions. Micrometeoroids are the silent assassins of space travel, fragments of asteroids and comets, zipping through the void at speeds up to 60,000 miles per hour. Orion encountered hundreds during its flight, but one cluster struck with unusual force. Post-flight analysis revealed craters up to 3 millimeters deep in the heat shield's ablative material, a specially designed epoxy resin meant to burn away gradually during re-entry, carrying heat with it. The concern wasn't just the pitting itself, but the location. Several impacts clustered near the shield's centerline, precisely where temperatures peak during Earth return. Had these pits been slightly deeper, they could have compromised the capsule's ability to protect astronauts from the 3,000-degree inferno of atmospheric re-entry. The mystery deepened when engineers realized these weren't typical micrometeoroids. Most are icy or loosely packed, disintegrating harmlessly on impact. These acted more like armor-piercing rounds, suggesting they might be metallic fragments, possibly debris from past spacecraft collisions, or even remnants of the Moon's volcanic past ejected into orbit. Whatever their origin, they exposed a flaw in risk calculations. Orion's shield was designed based on statistical models of micrometeoroid flux near Earth, but the lunar environment, with its lack of atmospheric filtering and complex gravitational traps, appears to harbor harder, faster projectiles. NASA's response was swift but sobering. Teams are now testing enhanced shield materials, including ceramic composites and self-healing polymers that could seal small punctures automatically. Meanwhile, mission planners are re-evaluating orbital trajectories to minimize exposure to known debris fields. The findings also prompted a broader discussion, with astronauts slated to orbit the Moon in Artemis II as early as 2025. Every design margin suddenly matters more. A heat shield isn't just a component, it's the thin line between survival and catastrophe when returning from deep space. What saved Artemis I from disaster was its unmanned status. The mission's unplanned stress test became a gift, a chance to uncover weaknesses before lives were at stake. As engineers pore over the data, one truth becomes clear: space doesn't forgive assumptions. Every crater in Orion's shield is a reminder that beyond Earth's atmosphere, even the smallest particles carry the energy of a bullet, and the margin for error is vanishingly thin. Future crews will ride on the lessons learned from these microscopic scars, proof that sometimes the most valuable discoveries come from what nearly went wrong. Far beyond the orbits of Neptune and Pluto, in the frozen darkness where the sun's light is little more than a faint star, lies a vast and hidden realm of icy remnants, the Oort cloud. This colossal shell of cometary debris, stretching nearly a light year into space, is the solar system's final frontier. Most of the time, these ancient ice chunks drift undisturbed, held in the sun's weak gravitational grip. But what if something, a passing star, a rogue planet, or even a galactic tide, jostled this reservoir of frozen projectiles? The result could be a cosmic catastrophe unlike anything Earth has seen in millions of years. Picture this: a gravitational nudge sends thousands of comets spiraling inward, a slow-motion avalanche of ice and rock set on a collision course with the inner solar system. This isn't science fiction, it's a scenario with chilling precedent. 66 million years ago, a single comet or asteroid, likely just 6 miles wide, slammed into what's now the Yucatan Peninsula. The impact unleashed firestorms, tsunamis, and a global winter that wiped out the dinosaurs. Now imagine not one, but dozens, or even hundreds of such impacts over millennia, a relentless bombardment from the depths of space. A disturbed Oort cloud could turn Earth into a cosmic shooting gallery, with each strike delivering enough energy to dwarf humanity's nuclear arsenals. The mechanics of this disaster are deceptively simple. The Oort cloud is thought to contain trillions of icy bodies, some as large as mountains. Normally, their orbits are so vast they take millions of years to complete. But a passing star like Gliese 710, which will swing within a light year of us in about 1.3 million years, could scatter these dormant comets like billiard balls. Once knocked loose, their journey sunward could take centuries, but the consequences would be inevitable. Earth's atmosphere would offer little protection against objects traveling at 30 or 40 kilometers per second, speeds that transform even modest chunks of ice into city-leveling fireballs. What's truly sobering is how little warning we might have. Unlike near-Earth asteroids, which we can track years in advance, Oort cloud comets often arrive unseen until they're already streaking through the inner solar system. Their long, looping orbits mean they could come from any direction, and their icy surfaces only begin to glow as they near the Sun, sometimes just months before a potential impact. The comet Hale-Bopp, for instance, was detected 2 years before its closest approach, a luxury we might not have with objects from deeper space. Yet within this apocalyptic scenario lies a strange irony. These comets, harbingers of destruction, are also cosmic time capsules. Their pristine ices contain the raw materials of the early solar system: water, organic molecules, even the building blocks of life. Some theories suggest Earth's oceans and atmosphere were delivered by cometary impacts billions of years ago. In a bitter twist, the same mechanism that might one day end civilization could also be the reason life exists here at all. The Oort cloud's hidden menace forces us to confront an uncomfortable truth. Our place in the universe is far more precarious than it seems. Unlike localized threats, supervolcanoes, earthquakes, or even solar flares, a comet shower is indiscriminate, unstoppable, and potentially civilization-ending. But it also underscores our growing vigilance. Projects like the Vera-C, Rubin Observatory, and next-generation space telescopes aim to scan the skies for these icy intruders with unprecedented precision. For now, the Oort cloud remains a sleeping giant, but its existence reminds us that the universe doesn't operate on human timescales, and that sometimes the greatest dangers come from the deepest cold. From the universe-shattering fury of the Big Bang to the silent menace lurking in the Oort cloud, we've witnessed explosions that defy imagination, detonations powerful enough to create galaxies, sterilize planets, and rewrite the laws of physics. These aren't just distant fireworks, they're cosmic benchmarks, reminding us that the universe operates on a scale where stars die in supernovas brighter than entire galaxies, where magnetars flicker for a millisecond and outshine our sun for centuries, and where a single impact can rewrite the destiny of a world. Humanity's place in this violent cosmos is humbling. We stand on a fragile planet, shielded by nothing more than a thin atmosphere, watching these cataclysms unfold across the void. Yet our curiosity burns brighter than any supernova. We send probes to sniff out comet debris, build telescopes to capture the last gasps of dying stars, and train algorithms to listen for the faintest ripples in space-time. Each explosion we study peels back another layer of the universe's secrets: how gold fills our jewelry, how planets form from stardust, even how life itself might owe its existence to ancient stellar explosions. But the real wonder isn't just the scale of these detonations, it's what they reveal about resilience. Supernovas forge the elements of life. Gamma-ray bursts, though deadly, might trigger the formation of new solar systems. Even Earth's greatest catastrophes, like the asteroid that wiped out the dinosaurs, cleared the way for mammals and eventually us to rise. Cosmic violence isn't just destruction, it's transformation written across billion-year timescales. Now we turn to you. Which of these explosions left you breathless? Was it the solar flare that nearly fried our technology, the Kilonova that sprinkled gold across the cosmos, or the dying star whose light reached Earth centuries after its death? Drop your thoughts below, and if these cosmic spectacles left you hungry for more, hit subscribe. The universe is full of mysteries, and we're just getting started. Until next time, keep looking up. The next Big Bang could be just over the horizon.